X-rays. The Crookes tube that led to the discovery of the electron also was instrumental in the discovery of X-rays. William Rankine noted that we had a screen coated with barium platinocyanide and it was less than 2 meters away from an operating Crookes tube, it would light up. He theorized that a radiation was being emitted from the metallic anode when the cathode rays, which were emitted from the cathode and were shown by Thomson to be electrons, struck the anode. Then the screen would glow. At this time, the dangers of X-rays were not known, and many demonstrations occurred which would not be allowed today. Over here, we have an X-ray photograph of the hand of Rankine's wife, Anna Bertha Ludwig. So what you're seeing here is the X-rays are going into the page, through the hand, and on the other side they have photographic film. What's happening is the X-rays are being absorbed by the bones, so you see these dark shadows, but they go right through the skin and they expose the photographic plate on the other side. You can see this over here, probably a ring of some kind. That would also stop the X-rays. The intensity of the X-rays would increase with a denser target plate or a denser anode. They penetrated skin and they left images on photographic paper as we just discussed. It was also discovered that the rays were not affected by electric and magnetic fields, so they did not have a charge, they were neutral. Understanding of the nature of X-rays came rapidly. In 1899, Hermann Haga and Cornelius Wind demonstrated X-ray diffraction through a narrow slit, just like what was done with visible light, and estimated the wavelength of X-rays to be about a nanometer. For comparison, visible light has wavelengths of about 700, 800 nanometers. This indicated that X-rays were waves. In 1912, Max von Laue showed X-rays diffracting through crystals, which enabled the study of the structure of materials. Then, in 1923, Arthur Compton showed that X-rays were acting as particles now, not waves, when low-intensity X-rays were scattered by electrons. There'll be more on this later. A year after Rankine discovered X-rays, Henri Becquerel noticed that uranium salts also emitted a type of radiation that exposed photographic paper. However, unlike X-rays, this happened without an external source of energy. Remember, X-rays were created when an electric potential was applied to a Crookes tube. Marie Curie and her husband Pierre conducted exhaustive experiments and analyses, and in the process they discovered radium and polonium, and they came up with a theory of radioactivity that showed that atoms were not indivisible. They were decaying into other substances. Curie, and Becquerel were awarded the Nobel Prize in Physics for this discovery in 1903. Marie Curie was the first woman to be awarded the Nobel Prize, which she shared with Henri and Pierre, the only person to be awarded the Nobel Prize in 2 technical disciplines, which were physics and chemistry, and the first woman faculty member at the École Normale Supérieure. Sadly, Marie's work led to her early death from radiation exposure. Subsequent research by Becquerel, Marie Curie, Pierre Curie, Rutherford, Andrade, Royds, and many others isolated 3 types of radiation that were emitted by the soon-to-be-discovered nucleus. Gamma rays, which were a type of high-energy ray, higher than X-rays, had a high frequency, and it arose from the excitation and de-excitation of protons and neutrons in the nucleus. Beta particles were electrons from beta decay in the nucleus, and this was the radiation from the uranium salts that we just talked about. You know there are no electrons in the nucleus from previous courses. However, beta decay is where a neutron turns into a proton and an electron, and the electron is kicked out as beta decay. That's a little beyond this course, but that'll be coming. And then alpha particles, which are just helium nuclei without the electrons.